Hello everyone, this is Damini from SVCE College, and here I'm here to explain you about the topic network analysis from linear algebra. Here are the topics that I'm going to explain: introduction to network analysis, key concepts in linear algebra of networks, matrix representation of graphs, adjacency matrix, Lapchian matrix, eigenvalue and eigenvector in network analysis, spherical graphic theory, application of linear algebra in network analysis. Then comes the conclusion. Introduction to network analysis. Network analysis studies system of nodes connected by the edges. It is used to model complex systems in various fields like social network, communication system, biology, and more. Linear algebra is an essential tool in network analysis, providing methods to study connectivity, centrality, and community structures in network using matrix, eigenvalue, and eigenvector. Key concepts in linear algebra for network: vector space, collection of vectors that can be scaled and added, matrix, regular array representation, relationship between nodes, adjacency matrix represents a direct connection between the nodes, degree matrix, diagonal matrix that shows the degree of each node, Lapchian matrix, difference between the degree matrix and adjacency matrix, eigenvalue and eigenvector, fundamental concepts used to extract important features of networks such as centrality and connectivity. Adjacency matrix representation. The adjacency matrix is a square matrix used to represent a graph where A of ij is equals to 1 if there is an edge between the node I and j. A of ij is equals to 0 if there is no edge between the node I and j. Example, I have given an example over here in the PPT. Then comes the Lapchian matrix. The Lapchian matrix of a graph is given by L is equals to D minus A, where D is the degree matrix and A is the adjacency matrix. And I've mentioned a few examples in the PPT. You can go through it. Then comes the eigenvalue and eigenvector in network analysis. Eigenvalue problems. For a matrix A, we solve the equation A into V is equals to lambda into V, where lambda is the eigenvalue and V is the corresponding eigenvector. In network analysis, eigenvector gives insight into centrality and influence within the network. Eigenvalue centrality measures the importance of nodes based on their connectivity and the importance of their neighborhoods. Eigenvector centrality example: a node with high centrality has many connections to other high centralities. Spherical graph theory. Spherical graph theory studies properties of graph using the spectrum of matrix associated with graph. Key concepts: fielder vector, the vector corresponding to the second smallest eigenvalue of the Lapchian matrix. It is used to detect communities or partition in networks. Graph connectivity. The eigenvalue of the Lapchian matrix reveals how well the network is connected. Smaller eigenvalue indicates weaker connectivity. Example: for a graph with a small fielder eigenvalue, uh, partitioning the graph into two clusters of often effective. Applications of linear algebra and network analysis. Community detector. Spectrum clunction based on the Lapchian matrix can identify group of clusters of nodes that are densely connected. Example: spherical constellation can be participation of network into communities based on eigenvector and Lapchian matrix. Centrality measures. Eigenvector centrality measures the influence of none by considering the centrality of its neighbors. PageRank algorithm based on the dominant eigenvector of the web hyperlink structure. Graph using the fielder vector of split network into connections, components or smaller subtitles. Graph connectivity. The spectrum of the Lapchian matrix reveals the robotic of the networks. If the graph highly connects, the Lapchian will have a second eigen value field. Examples of spherical clustering. Uh, Given undirect graph, we can use spherical clustering to find cluster based on the eigenvector and Lipschitz matrix steps. Calculating the Lipschitz matrix, L is equals to D minus A. Compute the eigenvector of L. Use the filter value of a partition of nodes into cluster. And here is one example for that. Challenges and considerates: scalability, eigenvector and eigenvalue computes can be communically expensive for large network. Dynamic network, real world network often change over time, requiring adaptive and real time analysis. Interpretation: eigenvalue and eigenvector can be challenging to interpret without a solid understanding of graph theory and the specific context of network. Then now finally I'm coming to the conclusion. Linear algebra is a crucial of analysis of network, offering a mathematical framework of understanding connectivity, centrality and community structures. Matrix representation like the adjacency Lipschitz matrix, allowing for the efficient analysis using tools like eigenvector and eigenvalue. Applications span across the various domains for the social network to telecommunicate, offering value insight into complex system. So that's all in this video. Let me meet you in the next.